So for our first module, learning module of Chapter 5, which really is a pretty short chapter, it's one of these things that we already built all the groundwork in Chapter 4, and really all that this is just defining the expanded conditions of equilibrium and really getting some experience working a bunch of practice problems. I kind of want to go over an overview of the chapter. So the chapter is about rigid body equilibrium, so this is just a broad overview. So in most practical scenarios, we've talked about this quite a bit up until this point. I kind of feel like we keep repeating a lot of the same ideas. In Chapter 3, when we did equilibrium problems, we assumed that we could model the body upon which the forces were acting as a particle. And as we said, that didn't necessarily mean that the body was small. What that meant, largely speaking, just for purposes of simplification, is that the line of action of all the forces acting upon that body passed through a common point. And we called that a concurrent force system. So when we said that whenever force systems were concurrent, that we didn't need to care about the physical size of the body in our model, nor where the actual forces were applied. We could just kind of lump it all in, test forces in a single point, and enforce equilibrium by just ensuring that the resultant force was zero. But in practical scenarios, that's really not the case. The force system won't be concurrent, and when that force system is not concurrent, we need not only worry about all the forces acting on a body tending to move it or translate it, but we also have to consider the fact that that force system will inherently tend to rotate the body. So our equilibrium conditions are going to expand. They're going to expand from just a condition that the resultant force be zero to a condition related to a moment. And as we'll see in the subsequent slide, maybe it's two in advance, that rotation-related equilibrium condition can be simplified to the sum of all moments about any point on the body being zero. So the one additional point I wanted to make, I've said this before, I think it was back in Chapter 1, when your book uses the term rigid body, what they're referring to is a system such that when the force is acting on the body, even though there is a little bit of deformation, meaning the size of the body changes, that size change is negligible and can be ignored from a modeling point of view. So the book spends quite a bit of time on kind of going over the workflow of general static modeling. The one thing that I want to make sure you're all aware of, and I'm sure you are, is this really is a back of the envelope type quick analysis. It might not feel quick when we have those pages of math going on, but it's not an overly rigorous analysis type process. If you move on in a mechanical engineering curriculum, once you get a little bit later, you'll go over techniques like finite element analysis that are more rigorous, where you actually use numerical methods and decompose systems into little elements, as you might expect, and enforce some system equations on each element, and through continuity are able to reduce it to some big matrix vector or linear system type approach. But for us, we're just doing back of the envelope type stuff. So what we're going to do when we have a scenario in the real world, kind of depicted as this truck bed on the figure to the left, we're going to come up with kind of a first stage simplification, which we have depicted here in the middle, which are what calls an idealized model. So an idealized model just takes the real world, which is relatively complicated, and makes whatever simplifications we can. Naturally, whenever you're going into two dimensions, right, that's a simplification in and of itself. And the idea is that once we have this idealized model, we have the capability to draw free body diagrams on it, where, again, the problem domain of statics is largely concerned with, is a given support structure sufficient to support a body under a given loading condition? The way that we're able to determine that is we replace the support structures with what are known as reaction forces. And the reaction forces that represent a particular support structure depend upon the type of motion that it can oppose. So if we look at the support system here, what we see is in this type of bed lift system, it's pretty obvious to us that one way that we could think about modeling the reaction force that's applied there at point A is something that only has the capability to overcome translation, right? Because we want it to be able to rotate about that point in order for the bed to go up and down. So it's not surprising to us that the corresponding supports there, the type of motion that they oppose is just translation. They need to allow rotation. In a similar fashion, when we think about this cable support of this bed that we have here attached to point B, we've hit on this point a lot. But the reactions that are applied by a cabling type system are always directed along the line of action of the cable. And that's because these cables, as we described, I believe it was in Chapter 3, can only support tension. They can only stand tension. If they were to be compressed, they would just collapse. So we're always going to know that the reaction associated with the cable applied at a particular point on a body is going to be a single force along the direction of the cable, kind of pulling away. So as we mentioned earlier, not to reiterate the point too much, but if we have a rigid body, that means that we're considering its distribution in space and its dimensions, and we have a system of forces and a system of corresponding moments or couples being applied to that rigid body. In order for it to be in equilibrium, we need to ensure that both the resultant force is zero along with the resultant moment. And if you notice in this description, along with these equations, that moment can be computed about any arbitrary point O on the body. So the resultant force being zero ensures that the body is not moving left, right, up and down, or in and out of the page. And the resulting moment being zero ensures that all of the rotations that those forces tend to induce kind of counterbalance one another. So in terms of representing these reaction forces in free body diagrams, this is kind of what I was talking about 3 slides ago. And of course, these are just simplistic models of the types of reactions that you would see in the real world. But the key thing that we need to realize is when we draw a free body diagram and we're interested in kind of answering this question of whether the support system is sufficient, the way that we determine that is to represent the effect of those supports by these reaction forces. And the reaction forces need to have characteristics such that they represent the motion that reaction can oppose. So in the case, if you have a pinned type connection, you can imagine that the rail in that case, the rod rather, late night, can rotate freely about that pin. So all that pin connection can really do is oppose translational motion. So that's why in this case, when we represent that by a system of unknown reaction forces, we only have an unknown X and Y component. If you have a system on a roller, clearly that roller can slide freely up and down, ignoring friction, that inclined plane. So the only reaction force will be normal to the surface. If we have a fixed support, you can kind of think of something that's actually anchored into the ground. Maybe it's like a 4x4 post where someone's dug out a hole and they poured concrete. Not only can that thing oppose translational forces, it can also oppose rotation. So in that case, we would model the reaction as consisting of both an unknown force in the horizontal and vertical direction, along with a unknown couple or moment. So the key point being, when you work these types of problems, the hardest thing to do oftentimes, if you can't see from the way that the drawing is represented, you might have to go to table 5.1 of your book and determine how you should model the reaction forces associated with each of the support structures. So just for a little bit of an example problem, assume that we have this assembly or this frame here. Maybe it looks a little bit like a truss. We'll look at that in a lot more detail in the next chapter. And assume it's supported in 2 ways. It's supported by a pin connection here at A, and it's supported by a cable connection at B. And those 2 supports are serving to offset the actual weight of this assembly. And we will apply the weight at the center of gravity, which we'll see more how to compute that when we get to the centroids of chapter 7. But the ideal being that, of course, you need this cable, because if you didn't have the cable, since that pin can't oppose rotation, the weight of that object would just tend to rotate it and it would flop down. So what the cable is doing is counterbalancing the tendency of the weight to rotate that about A. And we'll kind of see what's going on here in a minute. Actually, we don't solve the free body diagram here, but it's good when you do these type of problems to build some intuition on how the individual reactions are serving to both counterbalance the load. In this case, the load is just the weight of the body along with each other. So if we were to represent this by a free body diagram, and in this case, the free body diagram was concerned with finding the reactions at both A and B, there's 2 parts. The first is, what should the unknown reaction forces look like at A and B? Well, since A is a pin, we know that it can't oppose rotation, so we will have 2 components of the unknown reaction force, horizontal and vertical. And since B is a cable, we know it's just the only unknown is the magnitude of that force, because it has to be directed along the cable. And you can kind of see how all of those reactions are going to work about. I don't want to say too much because we'll get into it in the next learning module. But the upward force at A and the upward component of the force at B are going to offset the weight of one another. And you're kind of going to have equal and opposite things going on in the horizontal direction. But long story short, here's the free body diagram in this case. Just note that the pin connection, again, it can oppose translational motion. So we have an unknown X and Y component. For the cable, we know that there's only one unknown since the direction is determined based upon the nature of that support. And don't forget the actual weight of the object, which is applied at the center of mass or the center of gravity. So I hope that was helpful in terms of an overview. As I mentioned, that's really all the new material that is in this chapter. So I think it will be well suited for me just to do a bunch of examples, which I'll start doing in the next learning module.